Picking up where Jennifer left off on solving the hanging chain problem, we're going to look at that parametric form of Bessel's equation. And we see from section 4.8 that the parametric form of Bessel's is here in this first line. And so comparing that to the equation that we have, we see that it fits perfectly. And in particular, I want to point out that since we don't see the minus p squared that shows up here in this third term, then we know that p is 0, and that's how we can determine that the Bessel function that we're going to use is going to be that J0 Bessel function, the 0 order Bessel function. So because of that, and because additionally there's a requirement that our solutions for x are finite in theorem 3. That fits what we're doing really well because we have a chain with a finite length, and so we only want finite solutions. And so those finite solutions occur when lambda is equal to this alpha j over 2 squared of L, where alpha j represents the jth 0 of that J0 Bessel function. So our solutions for the x function are going to be these 0 order Bessel functions of alpha j over 2 squared of L s. So we also want to take a good look at the orthogonality relations from 4.8. This is those relations as they are written in 4.8, although I'm missing here that in this relation, alpha pj and lambda pj and lambda pk are not equal. The j is not equal to k. So in that case, when the j is not equal to k, we have 0, and when j is equal to k, then we have j squared, and so j squared of, in our case, it's going to be the J0 squared. But in any event, these two orthogonality relations become, these are orthogonality relations for our specific case. Okay, we have J0 of alpha j over 2 squared of L and alpha k 2 squared of L, again, where j is not equal to k, that's going to be 0. But when they are the same, there we go. When they are the same, then we have J0 squared of alpha j over 2 squared of L s ds, and that equals the 2L times the J1 squared of alpha j. So that's the Bessel function of order 1. So these orthogonality relations are going to be really useful when we find our coefficients. So now we're ready to substitute our 2 squared of x back in for s. So our x function is now x of 2 squared of x. And so that's going to equal the J0 of alpha j times the square root of x over L. So again, the orthogonality relations are here, okay, just basically taking what we talked about a second ago and putting in that 2 square root of x, and what gives us this. So putting together our t function that Jennifer found for us and the x function here, we have the product of x times t is going to be our u sub j function. So this product represents the normal modes of the chain. So u1 is the fundamental mode or the first normal mode, and these are kind of analogous to the vibrating string case situation that we talked about, I think, in chapter 3, where if you have the string that's vibrating on its full length, that's the fundamental mode, and then if it has a fixed node in the center so that it's got 2 vibrating halves, then that's the second mode, and so on and so forth. So same type of idea, but now we're, instead of a string fixed at both ends, we have a hanging chain. So if we need to find the frequency of any of these normal modes, then we use this formula here, alpha j over 4 pi square root of g over L. We're going to use that on the example. We're going to use it in the homework exercises where we are asked to find the frequency of the first, I think the example is the first 3, and then in the exercises, I believe it asks for the first 6 normal modes. As always, we're going to use superposition to get our final solution to the hanging chain problem as we see here. So now we want to determine our coefficients. We'll start with A sub j, and in order to do that, we're going to use the initial position of the chain, which is defined by f of x. So f of x is equivalent to u of x 0. So we set t equal to 0 in this function, and it reduces down to this. So now to solve for a, we're going to multiply both sides of this equation, the f of x and the sum on the right, by j sub 0 of alpha k square root of x over L. And then we're going to integrate that on both sides with respect to x from 0 to L. And those orthogonality relations are going to be really useful, because if alpha j and alpha k are such that j does not equal k, then this whole thing equals 0. So the only alpha k's that really matter are when they are equal to the alpha j's. And so that gives us the second orthogonality relation that we talked about. And so we integrate, we get the solution to the integration, then we solve for aj, and we get this 1 over L j1 squared alpha j integral from 0 to 1 of f of x j0 alpha j square root of x over L dx. So the 1 over L j1 squared on the left, that comes from integrating using that second orthogonality relation. So here's aj, and then a very similar process will give us the bj terms. The b's are coming from the initial velocity of the chain. So the initial velocity is the derivative of u with respect to t at x0. And so we do the very same thing. We multiply both sides by the j0 of alpha k square root of x over L, just like before. And again, the parts where j does not equal k are 0, and the parts where k is equal to j gives us that second orthogonality relation. And so solving for bj, we get this. So this gives us the entire solution for the hanging chain problem. So what we want to do in example 1 is we want to look at a chain of length 1 that is hanging from one end, and we're going to displace it in the middle 0.005 meters. So again, like with the vibrating string, we want our displacements to be pretty small so that those angles created are small, because remember we were able to go from the sine of those angles to the tangents of those angles, because dividing by cosine was essentially like dividing by 1, because we had really small displacements. However, when you look at the graphs in Maple, if you scale the axes 1 to 1, then you can barely even see the displacement at all. So I'm leaving all of my pictures and things in Maple, all the animations with axes that are not scaled 1 to 1, so that we can actually see the motion of the chain a lot better. So this is our initial displacement. We see that the middle of the chain has been pulled 0.005 meters, but really it's probably a little easier if I rotate the picture so that it actually looks a little bit more like a hanging chain. So we're fixed at this end can hang freely, and we're displacing the chain to the right 0.005 meters. So I want to kind of maybe tease you a little bit with a little video that I've created where I'm actually displacing a chain and comparing it to the final animation that we're going to get here in a minute. So you can kind of see that it's a little, it's kind of exciting. The math that we're doing actually does simulate the real world scenario. It's not quite a perfect comparison for a number of reasons. The chain that I'm using is probably brushing up against the wall a little bit and slowing it down, and the weight of the chain compared to the friction, maybe reducing the action a little bit of the wave, or of the swinging back and forth of the chain. But here's that video. I think you'll find it kind of interesting. So with this demonstration using my son's toy chain, what we want to try to do is mimic the behavior of what's happening in example 1, where the chain is displaced at about the halfway point, and it's only displaced 0.005 meters, which is less than what I'm doing here. But I'm going to split screen with the maple animation, and we can see that even though our toy chain doesn't have quite as much action as the maple animation, we can see that the behavior is very similar, which is pretty interesting, particularly at the kind of the extremes when the wave reaches a peak. Okay, let's look at how I got that animation that I showed you in the video a moment ago, because this requires, I think, a lot of Maple's computational power. Finding all of these zeros of the Bessel function and then calculating the integrals needed for A's and B's and whatnot. Maple is a huge help for this. So first thing we're going to do is we need to figure out what these alpha sub j terms are, which are the zeros of the Bessel function of order 0. So in Maple, the Bessel j function is what we're looking for. So in this case, I'm just solving for the first 3. So we have, again, where we have to tell Maple a number somewhat close to the zeros to help it calculate when there are multiple zeros. So I fed it 2.5, 5.5, and 8.8 just by kind of checking out the graph, and I found the first 3 there. So now the next part of example 1 was to find the frequencies of the first 3 normal modes. So just using that formula that I shared in the slides a second ago, we have alpha k. I'm using k from 1 to 3, so alpha k divided by 4 pi times the square root of 9.8. We're using 9.8 for g according to the textbook. So we get these values for the frequencies of the first 3 modes. And then next I wanted to take a look at f of x. And this is one of the things that is maybe a little challenging about this section in regard to Maple is, as far as I can tell through the research I did, there's no way to tell Maple that you want the x-axis to be vertical, in other words, the independent variable to be on the y-axis and the dependent variable to be on the x-axis. If there's a way to do that, I couldn't figure it out. So all of my animations are horizontal, and all my graphs have basically a hanging chain, but hanging from the right instead of hanging vertically like we'd like for it to be. So that, like I said, it's one of the challenging things about using Maple, just because it doesn't have the same visual effect. So like in the video I showed you, I had to screen record the animation and then rotate it to get it to look the way I wanted it to look. So, but anyway, here's f of x, the original position of our chain, but again horizontally. And so now I'm calculating each of these a coefficients, a1, 2, and 3. And again, Maple's a huge help here, because having to evaluate the Bessel functions, square the Bessel functions, integrate the Bessel functions, Maple does that a whole lot quicker than we can. And then we don't have any b terms in this example because we have no initial velocity. So the b coefficients are 0. So we can put together our u1, u2, and u3 products just with the a1 and the x equation there, the Bessel equation, that is our x equation. So this is the graph of the first normal mode. Here's the graph of the second normal mode and the graph of the third normal mode. So this should be just like what you see in the text. For example, 1, they gave us 3 graphs, and we see that our graphs match the 3 graphs in the textbook, so that's encouraging. And so now we can put those together. Now, when I tried to do the animation the first time, and I used all these definitions, the U1 with the A1 and the alpha 1 and all that stuff in there, I got an error message saying that I had too many levels of recursion. So I don't know why, but it seemed that Maple was going back and calculating each of those terms or something for every frame, and that was more than it wanted to do. So instead, I just typed in the values for each of these terms. So the 0.003847 you see is the A1 coefficient. So I'm just going through and typing in the numbers, a little inconvenient, but it fixed the problem, so went with that. So here's our animation, and again, the animation is horizontal instead of vertical, but we can see that kind of whippy action that we get from the hanging chain. Looks a lot better when I rotate it for the video, but there you have it. So that's how Maple helps us to get that visual representation there, that visual for the hanging chain.